Okay, at the end of that song, I think we'll probably get going. Hello, everyone. I am Nancy. I am manager and one of the statistical consultants at Stat Central. Today we have a special seminar for you today. Gordana, one of our other consultants, is going to be talking to us about practical study design. And this is a really, really important thing for people who are doing their research design and just starting out in their research careers. It's something that we as consultants encourage all people, particularly HDR students, because they're just learning how to do research, that this is a really important part of their research. So we thought it was worth not sort of truncating and making a very short presentation, because there's so much that's really important in this topic. This will be a 2-hour session. So we hope that you'll be able to stick around for the whole thing. Also, if you do have questions, I think that probably Gordana would be okay with answering them as you go, rather than waiting the entire 2 hours. So please, if you have questions, you can put them in the chat, or you can put up your hand, or even unmute yourself and go, wait, please, can you go over this again? Please, let's hear what Gordana has to say and enjoy the talk.
Thank you, Nancy. I want to start by mentioning that I'm on Badigal and Gadigal land, and that's where I live and work, and I pay my respects to elders past, present, and emerging. The other thing is when I'm teaching online, helps me a lot if I can see a couple of people's faces, because then I know how confused everybody is, or at least I have some idea. So if you're brave, turn on your camera, please. Yeah, just hang out with me with your camera on if that's what you want. Also, anytime you want, a couple of ways of asking questions. You can just put up your hand, which is in reactions. There's a little hands up, and one of these guys will notice, I probably won't, and they'll tell me that you want to ask a question, or you can type it in the chat if you like, and somebody will be looking at the chat and will ask me the question. Oh, wonderful. Thank you for those turning on cameras. Lovely. Okay, so practical study design. So I've built up this seminar over time, so there are different sections. So we'll start out pretty slow, just explaining the very basics of study design, like populations and samples, confounding and dependence, this kind of thing. So that's the first part. And then we'll try to do a little bit of study design with us. So when you're planning a study, you often want to randomize participants. So I'll show you how to do that. And then you might want to work out an appropriate sample size. So I'll show you how to do that. And then this bit says advanced study design, but definitely stick around for this bit, because this bit is where you learn how to get something for nothing. So you get to increase your power without increasing your sample size. So that's the bit that's kind of really good or really helpful sometimes. And then the really advanced study design is just some more advanced things like simulation. So if you kind of estimate your sample size, you need to do so by simulation. I'll talk about that a bit, and factorial designs and other bits and bobs of advanced stuff that you can do. All right, so let's get started. Okay, so the very first thing you need to conduct any research is a really precise question. So you need to know exactly what you need a couple of things. So first, you need to know who your study population is. So if you're in medicine, are you interested in all diabetics, or are you interested in diabetics that don't respond well to insulin? Or if you're an ecologist, do you want to know about this particular species everywhere or just that species in New South Wales. And so you need to have a very specific idea of what your study population is. And also in time and in space. And then what you need to know what your response variable, dependent variable, outcome variable is. So this is the thing that you're measuring that you're interested in. So if you're in medicine, it's some sort of measure of health, usually like blood pressure or whether or not somebody has a disease or whether or not someone dies. If you're in ecology, it might be abundance of something, or if you're in psychology, it would also be some like measure of depression or something like that. In engineering, it might be like how good whatever you made is when it fails a test or something like that. And then you've got your independent variables, and these are also known as predictors. And these are the things that influence your dependent variable, your response. So you need to know what specifically you're measuring that's going to impact your response. And you need to know which response that you're most interested in. You might be measuring heart pressure, you know, a bunch of things in the blood, you know, like you might do bloods on them, they might get 17 different things. You need to know which is the one that you're most interested in, or 1 or 2 or 3 that you're most interested in. Which one are you going to plan your study to study? That way you can actually do a proper study design. If you don't have an idea of which thing that you're measuring you're most interested in, it's impossible to plan a study to do all of it. You can incidentally measure the other things and still might be able to answer questions about them, but just to plan the study, you need to know which things are really important. And then you need to kind of have an idea of what the relationship is between the predictors and the response. Yeah, once again, you need like a concrete list of these things in order to plan a study. Okay. So a little bit about populations. So in statistics, we talk about this thing called a population, and it's not the same as a population is in sort of normal life. And we talk about it in relation to a sample. So a population is every possible observation that could have happened. So that's on the right. And then the sample is just the ones that we measured. So the ones on the left are the ones that we measured. So we went and measured 4 of these things, and two of them turned out to be blue and 2 of them turned out to be red. Okay, so, but we don't know what the population is. What we want to know is what does the population look like in terms of the proportion of reds and blues? But all we have is this sample. And in this sample, the reds and blues have an equal distribution, right? It's 50-50 in my sample. So my most likely population based on this sample is that it's about 50-50 in my population, right? But that doesn't mean it isn't 50-50 in the population. It's a small sample. And if I had this population and if I'd randomly taken 4 of these dots for my sample, I could also have quite possibly gotten a sample with 50-50 red and blue. So we always only know what we've measured in our sample, but we're never interested in the sample. We only are interested in the population. We use our sample to inform what the population might look like. So this is a possible population. And then if we had a larger sample, of course, then if we took 8 dots out of this population on the right here, it's pretty unlikely I would get 4 blue dots. Now that the scarcity of blue dots makes me think that it's pretty unlikely, whereas I could have gotten 2, but getting 4 is kind of on the edge there. So I'm thinking this sample probably doesn't come from this population. It could, but it's probably not the case. And that's kind of how statistics works. You look at the sample and you try to infer things about the population, but you can never be sure, and you just try to do as best you can. And then you have an idea of how uncertain you are, because this population is still possible. Okay. So samples and populations. So usually normally we talk about biological populations. So that might be, you know, people, you know, from the same country or animals from the same species, but that's not necessarily what a population is in statistics. It's just a collection of all possible observations. So in the previous thing, it was just all the dots that I could have sampled. Now, the characteristics of a population, for example, the population mean, are called parameters. Parameters are the things that I want. So in this example, what I'd like to know is the true proportion in the population of blue dots. Which is, I don't know, maybe like 10%. That's what I want to know. But the only thing I do know is the proportion in my sample, which is 50%. So the sample is just the collection of observations that we observed, and the characteristics of a sample are called statistics. So the sample mean is a statistic, and this is where the word statistics actually comes from. We calculate statistics from a sample, but we are never actually interested in the sample mean. The sample mean is just the mean of that sample. We're interested in the population. We want to know how well can we estimate the population mean if we have this sample mean, and that's what statistics is all about. Okay, so some things that might cause us problems. One of them is confounding. So confounding means that the differences due to either experimental treatments or predictors cannot be separated from other factors that are causing the observed differences. So here is an example, and maybe I'll try and get you people to type in the chat. So get ready to type in the chat. So you measure the height of some children. You go to a school and you pick a bunch of children at random and you measure their height and you give them a maths test at the same time. And then you get your sample of students from this population of the school, and you conclude that taller children are better at maths. This is like exactly what would happen. You would conclude definitely that the taller children are better at maths. So what am I missing here? What is the variable that is actually kind of causing taller children to be better at maths? So that's what you type in the chat. Let's see if anyone's brave. Chat. Where is my chat? Oh, here we go. Oh, so many people. Excellent. Awesome. Age. Exactly. So older children are taller, because that's how life works until you're very old. And also older children have gone to school for longer and learned more maths, so they're going to be better at maths. So it's not that the height is making them better at maths. It's just height is incidental to age. And also being better at maths is something that comes with age. And so there's this confounding variable, which if you didn't take into account this variable, you would conclude that height is important for maths ability. And so that's really important to think about in your experiments. Obviously, in this example, I made it so that you would all, you'd be able to guess what the variable is. But usually when we do research, you do it in a field where you don't really know that much about the system. And so it's sometimes very hard to know what variables could be confounding the relationships. Okay, is there a question? I can hear some talking, but it's very quiet.
I think it was somebody joining and I muted them.
Ah, wonderful. Okay. So, what can you do to remove the effects of confounding? If you'd really like to know if height impacts, causes kids to be better at maths, to remove the effect of the confounding variable of age, you have two options. You can conduct a manipulative experiment, or an experiment, I guess is another way of saying it. And this can completely remove the effects of confounding. And I'll show you how to do that. And you can show causation using this method. In observational studies, which means that you collect data, but you don't do it in a manipulative manner. You don't say this person's in this group and this person's in that group. You can also control for confounding variables in the analysis. Now, for this to work, you have to measure all the possible confounders. So you have to know what they might be and then measure them in order to control for them. So this never works 100%, and we never know that we've measured all the possible confounders, and that's why you can't show causation from observational studies. All right, so what's this manipulative experiments? So if you're in medicine, these are called randomized control trials. In other places, they're just called experiments. So to conduct a successful experiment, you need three ingredients: controls, replication, and randomization. So controls. So lots of factors can influence the outcome of an experiment: the weather, aliens, stress, and they're not under our control. So we need to know what would have happened if we had not given the experimental manipulation. So if we give people a treatment and we want to know what is the effect of that treatment, we need to also know what would have happened if we hadn't given those people a treatment, so that we can compare the two groups. And so the way we do that is we have controls. We have a group that doesn't get the treatment and one that does. So that's a control. Replication is necessary so that you can attribute differences between treatment and control to the treatment, rather than to innate differences between the subjects. And replication is also related to confounding. And then randomization, this allows you to overcome confounding as well when measuring a treatment effect. Because regardless of any confounders, the probability of being in a treatment group is equal for all participants. So that's when we randomize, we make that probability equal, and that removes all the confounding due to the confounders. Okay, so controls can are often done in clinical trials, and generally speaking, what you want to do is make sure that the controls are in every possible way exactly identical to the non-controls, to the treatment group, except for the treatment. So the treatment should be the only thing that differs. So then when you say, well, there's a difference between these two groups, you can say the difference is because of the treatment. If there's multiple things different between the groups, then you don't know if the difference that you observe in the outcome is because of the treatment or because of these other differences between the groups. So in clinical trials, people are given like a sugar pill and they don't know that they've gotten a sugar pill and they think they're being treated with a medication. In predator exclusion experiments, you might exclude some predators, but not others. And yeah, so you also, the other reason that you give a sugar pill to people is this weird thing called placebo effect, which probably most of you know about. But essentially, if you feel like you're getting treated for something, you get better physically and mentally in many ways, even if that treatment doesn't do anything. So this has to be accounted for. Okay, so replication is clear to almost everyone, and then there's always some people who have at some point gotten the wrong idea, or somebody has given them the wrong idea about replication. So this might all seem obvious, but here's an example. So we have some rats, and we have two treatments. So I'm going to call these treatments, but it's just a genotype actually. So there's the brown treatment and the blue treatment of rats. Right. And so what do? I take a rat from the brown group and I produce some measurements of that rat. And I've got 3 measurements from this rat, and then I do the same for the blue rat, and I've got 3 measurements from this blue rat. So I can do that, or I can, instead of that, take 3 rats from this group and take measurements from each of 3 rats in this group and each of 3 rats in this blue group. So the thing to notice is that in either case, I'm going to have a spreadsheet with 3 rows that are brown and 3 rows that are blue. So my data sheet is going to look identical in this experiment and this one. And then I'm going to do a t-test or something. And if I do a t-test in this experiment, all I will be able to say is that this brown rat, this particular rat here, is different to this particular rat there. I won't be able to say that the brown rats are different to blue rats because each rat is different from each other rat. So I can't make that claim at all. So the replication is necessary so that now I have 3 brown rats and 3 blue rats, and I'm comparing these groups of blue rats and brown rats, and that makes me able to say that this is because of the treatment and not because these rats are different rats. Okay. Any questions about that at this point? Oh, okay. So many of you will be doing observational studies. There is quite a bit of study design involved in observational studies, and people don't often think about it because it seems like you don't get to, randomize, you don't get to do a lot of things that you should be doing. And so there might not be study design, but there's actually lots to think about. So observational studies, well, like we said, they don't give you the same level of evidence as manipulative experiments, and they can't prove causation, but often they're the only thing that is available. For different reasons, ethical reasons, where we can't randomize people to smoke, for example, because of cost. Randomized control trials are incredibly expensive. Or if you have rare outcomes, you might do a randomized control trial and nobody might get the outcome that you are looking for, and then you've wasted all this money. So there's lots of reasons why you might want to do observational. And even if these are not the case, observational studies are a really good way to generate hypotheses that you can then later on test in a clinical trial. So they're really good things to do in general. Okay, so here are a couple of different types of observational studies. So the basic ones are cross-sectional, case control, and cohort. And I guess there's different ways of grouping these, but this is what I've gone with. So cross-sectional means you go out and you collect a random sample of, say, people. You just go, you're interested in how, smoking relates to their blood pressure. And you go and you find some people and you ask them if they smoke, and you measure their blood pressure on the same day, at the same time. So this is cross-sectional. And it's the fastest, sort of cheapest way to do an observational study, but it has many bias problems. You don't know, for example, which came first, the ill health or the smoking. What else is going on with these people? Why are they smoking? There's many other reasons. There's many confounding variables. People in certain demographic groups smoke more than others, and so those are confounding variables in this study. So it's very hard to pick that up, but you can get associations that you can then use later on to generate hypotheses and do a trial or a better. Yes, sorry, there was, Nancy's answering questions. Okay, so that's a cross-sectional trial. Then there's case control, which are retrospective. These are often done for rare outcomes. So if you're treating a group of people that have a rare outcome, say in medicine, you find these people, you might only have 20 that you have access to. And if you took a random sample of all the people in Australia, there's no chance that you'd get any people in this particular group. So you can't do that. So what you're going to do is you're going to find these 20 people that have the outcome. So they have this rare disease X. And then you will look for some people that are in every way similar to these people, but they don't have this disease X. And you try and figure out what are the differences between those two groups. Okay, and obviously there's a lot of bias that can occur in how you choose controls and all of this stuff. But they're good for rare outcomes. And then there's cohort studies, and these are the best sort of studies that you can do in terms of observational studies, because you follow people over time. So you find some people, some of them have and some of them don't have an exposure like smoking, some smoke, some don't smoke, and then over time you see if they get, high blood pressure or other diseases. So you can estimate the temporal association between exposure and outcome. But of course, they're much more expensive. And then there's issues like loss to follow-up. Some people just don't come back to be followed up. And what do you do with those people? You don't know if they died. You don't know if they got sick. Okay, so these are the types of observational studies. So there's a couple of things you have to think about with observational studies. Obviously, confounding is a big issue because you can't randomize. You have to think about all the possible confounding variables that are going to be present in your study, and then try to control for them in your analysis. Obviously, we can't ever know what they all are, so we can't infer causation. So there's that. The other thing that goes really badly in observational studies is how you define the control and treatment groups. Say you're interested in how smoking affects the risk of lung cancer. And so you have this database of people, and you've measured whether or not they smoke and their age and sex and a bunch of other things, and you have an idea if they got lung cancer. So you want to know what is the effect of smoking on lung cancer. So what you'd like to do is create a group that's not smoking, non-smoking, and a group that's smoking. There's a million different ways to actually do that with observational data. So do you define somebody as smoking if they've ever smoked? And what if they started smoking after are you going to take into account if they started smoking after they got their lung cancer diagnosis or before they got their lung cancer diagnosis? Do they have to smoke for a period of time, say 5 years? Do they have to smoke a certain amount for you to include them in the smoking groups? There's a million ways to make this decision. And each of those will include different biases in how in what your analysis is going to eventually be. So it's really important to think about how to create these groups in an intelligent way. So I saw a talk once, and so I'll tell you one way to do that. This is called a target trial. So what you do is, you'd really like to do a clinical trial to answer your question, because you know that that's the best form of evidence. And if you had infinite money, and if you had, you were allowed to give people cigarettes and make them smoke without causing them damage, that's what you would do. All right, so you have this clinical trial in mind that you'd like to do. So then you write it down. You write down your eligibility criteria. For example, if somebody already has lung cancer before they start the trial, well, they're not eligible, or there's other eligibility criteria. You're going to tell them in this case there's no treatment, but whatever treatment strategies might be. So if you're, instead of doing smoking, if you're looking at the effect of some antidepressant, for example, then you might have a treatment strategy, how you're going to assign people to groups, follow-up period, outcome analysis plan. You do all this as if you're going to run this trial. And then you look at each of your people in your data set, and you look at them in their first year and you say, do they meet the eligibility criteria? No. What about in the second year? No. What about in the third year? Yes, they meet the eligibility criteria. Now they're in the trial. So this is now that person is now in that trial starting in year 3. And you do that for each of your people. So then you have a start date for each person. And then you don't care if the outcome happened to them before the start date. So if they got, if any outcome happened to them before the start date, that's before the trial. So it's not something you would include in the trial outcome. So you only look at their outcomes after you start them in the trial. And that way you avoid a lot of these problems about sort of choosing how to separate these groups. Now you're going to fail in trying to implement all of these criteria, because it's observational data. You're not going to have all of the things that you'd like to measure or know about these people. There's going to be lots of problems, but you just document these. And then you can very clearly say, well, this is the deviations that I have in my, my example from what I would ideally like to do. And then that way it's all very clear what's been done. So I quite like that idea. It gets you to write everything down and have a clear plan for how you're going to do these things. Okay, so how are we doing for time? About half an hour. It's pretty good. Okay, so I'm going to have a little section. Okay, so this is with R. If you're not an R user, I have some links as well for how to do these things without R. Okay, so maybe I'll stop for questions. Were there any questions so far? Okay. All right, so so what we want to do is we're designing an experiment, and we have 2 groups or 3 groups, but say we have 2 groups, and we want to be able to put people into groups. And we want to do this in a random way, and because randomization is going to mean that we have no confounding. And so, yeah, okay, I've talked myself around. Anyway, so first I'll talk about independence, then I'll go to that. Sorry about that. So independence is a concept that means that knowing the value of one unit, of one observation, doesn't tell you anything about another observation. So the way that you have dependence, it might be animals in the same aquarium, because they're exposed to similar conditions are dependent. They're more similar than animals in different aquariums. Or measurements from the same person are obviously going to be more similar than measurements from different people. So multiple measurements from the same person. Or if 2 people or 2 things are close together in space or in time, they tend to be more similar than if they're further apart. So these are all types of dependence, and we'd like to take these into account. And then independence can be guaranteed by random sampling in the manipulative experiments and random allocation to treatments to subjects in manipulative experiments. Oh, okay, maybe I need to drink some water. All right. Okay, so what I'd like to show you is how to do this random allocation of subjects to treatment. So if you're doing a RCT, you will have to do this. Like it says in the protocol, you got to do it. So you'll figure it out. But in many fields where you're not doing like a very official RCT, you're just doing an experiment with rats or something like that, people will ad hoc randomly allocate subjects to treatments. And I just want to show you, like, it's pretty easy to do it properly. And so you may as well do it properly. All right, so if you want to basically allocate patients to treatments, there's a couple of online tools that you let you do it easily. If all you want to do is basically you've got 2 or 3 treatments and you want to allocate 50 subjects to 2 or 3 treatments, you can use one of these. I'll give you the notes afterwards. If you want more complex randomization, I've never done it, but REDCap seems to have quite a few tools for that. Also, Excel is quite good. And one of us can show you how to do it in Excel. So if you want to talk to a statistician, we can just show you how to do it. And that's for more complex stuff, but the easy stuff you can sort of do with the online tools. Okay, so what about in R? In R, there's this package called randomizr. And so we'll install the package and then we'll try to allocate some subjects to treatments. So what you do is there's this complete random assignment function, and it assigns n subjects to num arms groups. So if I know how many groups I want, all I need to do, so if I want to assign 100 subjects equally to 4 groups, I just go n equals 100, num arms equals 4. And then if I do, so that will saved into Z. And if I do a table of Z, I see that I have 25 people in each of the treatments. So that's good, but who is in which treatment? Well, if I look at Z, I can see that the first person is in treatment 3, the second one is in treatment 2, and so on. So this gives me the treatment of each of the people in my study, allocated randomly. So it's super easy to do in R, if you're an R user. So that works if you know the exact number of subjects beforehand. Sometimes you kind of don't, you've collected some, you've got a few, you started recruiting for your trial and you have 25 people or something, but you know you're going to keep recruiting. So you don't exactly know how many people will be there. So you want to start randomizing the ones that you have. So then you can do this. Oh, no. Okay, so that's that one. If you want to do that, I've talked myself around again. Apologies. Okay, so the first thing is if you don't want equal allocation to treatments. So if you want more people in one of the treatments than in the others, you can easily do that with this m each variable. So I want 20 in the first group, 30 in the second group, 50 in the third group. And I'm also going to name my conditions, my groups. I'm going to name them A, B, and C, just so that I don't have this T1, T2, T3 business. I know exactly where I am. So C, B, B, these are the groups that each of my subjects is in, each of the 10 subjects. And I can see that there's 20 in group A and 30 in group B and 50 in group C. Okay, so now if I don't know how many subjects ahead of time, I can do it with some probabilities. So say I have 100 subjects, but I'm probably going to recruit some more. So I don't really want exactly the same number of subjects necessarily, and I don't know how many I'm going to have. Or I might not even have 100 subjects yet, but I might want 100 subjects and I want to know what happens to the first ones. I can put in probabilities instead. So I can say, well, I want 20% in the first group, 30% in the second group, 50% in the third group. And then this simple RA will give me that if I use the prob each argument. So now I don't have exactly 20, 30, 40, but the probability for each subject is 20, 30, or 40. So this is sometimes useful as well. Okay, so that's how you do it. That's how you would allocate subjects. That's what I do. If somebody comes along to Stat Central and goes, can you please do a randomization plan? I would often just do that. Very simple. Questions? Okay. Okay, so what about sample size? So sample size is the next thing to think about. So once we have a design that has all the properties, you have a clear question, you have some controls, you have replication, independence, we still need to decide on a sample size. And to do that, we need to know a couple of things. We need to know the effect size that you're interested in, which we'll talk about in a second, as well as what variation there is in your data, what variation is naturally there in your data. So what is the aim of a study? Well, one aim is to detect an effect if one is present. So remember, we always have a sample and we want to know about the population. So we want to be able to use our sample to say something about the population. And if in the population there is an effect, we want to be able to find that effect. So that's what we want to do. And if you fail to find this effect, it's called type 2 error or false negative. So there is an effect, but we didn't find it. And the most common reason that you don't find an effect when there is one is that you have a small sample size, or your sample size is too small. Okay, so there's no point in running an experiment if you have very little chance of detecting an effect. So if we have some information, so even if you, a lot of the time for ethics or for grant applications, you will need to do a sample size, and so you'll do it. But a lot of the time you don't need to do it. In many types of experiments, you don't have to do a sample size. You just kind of come up with it at the top of your head. But if you have an idea of effect size and variability, you can still do a power analysis, and it'll give you a lot of information about what sample sizes would be reasonable to be able to detect that effect. It might save you months and months or maybe years of time. Okay, so the best way to estimate, so we need two things. We need the variation and we need the effect size. To estimate variability, there's a couple of things. Ideally, you would have a pilot study, and that will give you the variability of your data. So a pilot study.
Gordana, we have
Yeah,
a couple of questions. Okay. Yeah.
Yeah, I'll just finish my sentence. So a pilot study is just, a small scale version of your real study that, you just do the same thing that you would have done in your real study, but you only have 10 or 15 people in it. And that will let you estimate, a couple of important things that will let you then plan your main study better. So, so there's a couple of questions. Could you give an example when you would use probability randomization? When would I use probability randomization? Often we use it when, so not in its plain sort of way, but it's often used when there are, what's it called, matching? When you want to match on different strata.
Yes.
Then you have to use probability randomization. But in a plain experiment like what I just showed, it's probably not that useful. I guess, yeah, I don't know when it would really give you a better answer if you have a sample size. Maybe one of my colleagues will speak up. What is power analysis? Power analysis is what statisticians usually say when they mean to say sample size estimation. When we do a statistics course, we call this power analysis because we want to know what the power is. But really, for most practical purposes, what you do is you try to estimate a sample size. I'll go through. So power. Sorry, let me just cough. I've been sick. Oh no, where is my mute? I have no mute. Here it is. Done. Okay, so power. So remember we said the aim of the study is to detect an effect if one is present, and failure to do so is called type 2 error. So if you don't detect your effects, then you're making a type 2 error. And power is the probability that you won't make a type 2 error. So you don't want to make a type 2 error. So the higher your power, the less likely you are to make a type 2 error. So that's what power is, and it's related to sample size. Does that kind of answer your question? Can you use probability randomization when I know that there is a larger probability in recruiting participants for one group than the others? You don't normally recruit participants If you're going to randomize, then you don't recruit participants usually you don't recruit participants for a particular group. But in terms of strata, if you're stratifying by if you're stratifying your participants, maybe you have more women than men and you want them to be equally in the groups, then that's a time when you would use probability randomization, yes. Okay. Alrighty. So yes, so in terms of variability, so you need these two things. You need an effect size and you need variation. If you're really lucky, you have a pilot study where you can estimate variation from that. If you don't have a pilot study, then variation like standard deviation and standard error are things that are often or should always be reported in other people's studies when you look at the literature. And so you can use these estimates in your sample size estimates. If you know the standard deviation and standard error and you can work out the standard deviation, then you can use that. Okay. Okay, so we're not doing any stats. Does it make any difference to power analysis if subjects are their own controls? Absolutely. Yes, it makes a huge difference. That will be in the advanced sample size, an advanced part of this course or this seminar in about 20 minutes. I'll talk about that. Okay, so when this course isn't about stats, but in order to do sample size, in order to estimate sample size, I do need to specify a test that I'm going to do. So the test that most people learn, the first test is a t-test. So basically, we've got two groups of measurements. There are people in group 1 are unrelated to people in group 2 and each other. And so these are given one treatment, these are given another treatment, and here is what they look like. And we're interested in it if on average the treatments differ. So that's what we want to know for these people. Okay. So we need an effect size. So in this case, so this is the magnitude of the effect that you're hoping to detect. And so if you have this kind of case where you have two groups and you're interested in their difference, then the effect size or the effect that you're trying to estimate is the difference between the population means. So that's what you'd really like to know. Is there a difference in the population means and how big is the difference between them? So that's the effect. Okay, so there's a good question. Sometimes sample size from power estimation is relatively large, for example, 100, but in reality, we don't have enough time and funding to recruit a large sample size. How do you make a balance to ensure statistically meaningful results? Yeah, so it's really hard, but there are ways to, sometimes you can, sometimes there are ways to improve your power without having to improve your increase your sample size if you do it intelligently. And so I'll talk about that in a minute, but also in that kind of case, definitely come and see a statistician. We're always really happy to help with these kinds of things where, we're most useful we're almost more useful at the study design stage than we are at the statistics stage. And we know lots about stats and we can help you with that, but it makes much more impact if you talk to us at the study design stage. Okay, so we want to know that true effect size, so the true difference between the population means. That's why we're running the experiment. So we don't know what that is. So to choose an effect size for the power analysis or the sample size analysis, I should probably say there, we need to consider what effect size is meaningful. So that might be clinically meaningful, biologically meaningful, ecologically meaningful, meaningful in your specific area of interest in your specific study. What would be meaningful? So for example, there might be a treatment that you're interested in, and that treatment might improve the outcome for people by 5%, but that treatment might be much more expensive, for example. So if it only improves the outcome by 5%, that's not actually clinically interesting. No one's going to actually use that treatment. So maybe a 10% difference is when you start to care. So maybe a 10% difference means that, okay, this treatment's actually going to be better. So that would be the effect size for your study. So people do quite often, it's very common to look at at the literature to find an effect size as well. And I do use it, and we do it all the time as well if there's no meaningful way to create an effect size. But there is, you do pay a price for that. So if you look at your previous literature and you find that the difference between the treatment and control groups was 5, say, but 5 might not have been relevant to you. So you're going to use this small effect size, and you need a much larger sample size to estimate a small effect size. So you're going to estimate, you're going to do your sample size analysis. It's going to tell you need 1,000 people. But if you'd chosen your effect size based on something clinically meaningful, then you might have chosen 10%. And then your sample size that you estimate will be smaller. So it should be something that's actually meaningful. And you can use the literature as a guide, but I do think you need to think about it in a what's actually meaningful for this study. Okay. Okay, sample size. To estimate sample size, if you're not an R user, the GPower app is free. It's relatively basic, but it'll do most basic things. I've run this same sort of seminar a few times, and one time I did it, I used GPower. So there's a video of that if you want to do if you want to have a look at that, if you want to use GPower. There's other things called that, for example, Pass is a package that's really good, has a free trial, but then it's super expensive. And that's what we use at Stat Central to do sample size analysis. But R is also quite good. Okay, so in R, we can do it with the Power, PWR package. All right, so we're still going to use this idea of a t-test because that's the sort of easiest test, just to show you some things. So we're going to use a 2-sample t-test. And what you do is you use this particular function is for a t-test, so power t-test. And it has 4 arguments. It has an n, a d, a sig level, and a power. And what you do is you fill out all of these except the one that you're interested in, and it will calculate the one you're interested in. So right now, I would like to know a sample size. So I want to know what sample size will give me a power of 90%. So that means that, so I'm going to need an effect size, but if that effect size, if the true effect size in the population is equal to what I specify, then power means that I will detect this effect 90% of the time with a 5% significance level. So I need all these ingredients. So I need the significance level. Usually we put that at 0.05 just because that's the most common thing that people do. The power, the common things are 90 or 80. These days we tend to go with 90 more often than 80. And then the sample size and treatment effect are the things that you're usually calculating. So one of these will be null. Okay, so significance level 0.5, power 0.9, so that's easy. And then I have to calculate an effect size. Well, I think of an effect size that would be clinically meaningful. So it might be 0.2. So that's the effect size that I think will be clinically meaningful. The effect size here is the difference between groups. So if the difference between groups is 0.2 or more on whatever scale that I'm using to measure, so maybe it will be heart rate or something, then I consider that clinically meaningful. Then I go to the literature or the pilot data, and I get an estimate of the standard deviation of the data. And so I'll need these two to work out this sort of standardized effect size, which is just a ratio of these two in this case. And I'm going to leave n as null. So I'm going to put in my effect size. I'm going to put in sig level and power, and I'm going to leave n as null, and it will calculate sample size for me. So if I do this, I get this output. So it says the sample size I need to have 90% power with a standardized effect size of 0.5 is 85 and a bit. in each group. So 86 in each group to be safe is what I need in order to be able to find this effect. So declare significance 90% of the time. So to have a 90% chance of declaring significance. Okay, I'll stop there for questions. Does anyone want me to go back and redo that? What do you do if you have no standard deviation from the literature? I can define my effect size based on minimum effect of relevance, but is there a way to do something like that for standard deviation? Look, you need to, there's no way, there's these things called standardized effect sizes. There's like a small, medium, large. T-shirt effect sizes is another way to call them. They're not great. They don't really mean a whole lot. It's because it's so dependent on how variable your data is. So there's always somebody that has measured the variable that you're interested in before you. I mean, there might not be, and in that case, you can't do a power analysis. But in most cases, the variable that you're measuring, the outcome that you're measuring has been measured in some form before, and somebody's published something with a standard deviation. So you just need to find it so that you can have an estimate of the standard deviation. How can sample size, sorry.
Yeah, I was going to say, yeah, there are a couple more questions.
Yeah, I see them. How can sample size be calculated from more complex models such as survival models? I'll get to that, it's hard. That's probably at the end of the talk. Usually simulation is the answer. Why does sample size depend on the effect size you expect to find? It's not the effect size you expect to find. Well, it is you expect to find, but it's the effect size in the population, because large effects are easy to find. If there's a huge difference between your groups, then even if you have 2 or 3 measurements in each group, you're going to very easily see that those groups are different. But if the difference is small, then you can't find that difference. You won't be able to notice that difference unless you have a very large sample size. So the effect size is really important. Can you please explain the trade-off between power and effect size again? Apparently I was slightly confused. Oh, good. So it's not a trade-off. So you have to have, you're usually aiming for a certain power, so a certain probability of being able to detect your effect. And the effect size just comes from your, well, it's something that's innate to your experiment or to your study. You know, like you are interested in detecting some sort of change or some sort of difference. And so you need to be able to detect, sorry, that number is, it is something. So it's not like you really, it's not a trade-off, but one does affect the other. So if you have a larger effect size, then you need less sample size to get the same power. What was sigma representative of again? Okay, that's a good question. Sigma is the variation. So this is just the standard deviation within groups. So if I have a look at my box plot, I mean, box plots don't really show you the standard deviation, but you know, it's how variable within the groups is. And that's what sigma is. So it's usually just how variable your measurement is within one treatment. Is there a unit for effect size? It's in the, so the way that I've done it here is that it's unitless because I've divided the effect size, which is in the same, the effect size that you are interested in finding is in the same units as the standard deviation of your data. So when you divide them, it's unitless, but they're both in the same units that you're measuring. And then when you divide them, yeah, it becomes a unitless thing. Yes, okay, cool. Good, any more questions? I think we're about there. Okay, so that was, okay, we're about an hour in. So this is the advanced study design that I did tease at the beginning where you kind of get something for free. So this is the good bit, I reckon. Okay, so there's two ideas called blocking and stratification, and I've tried to divide them in my head, but whenever I read something else, they use them in the opposite direction to what I'm used to. So I'm just going to say that blocking and stratification are the same thing as far as I can tell in the way that they're normally used. Okay, so random allocation of units of experiments. So if you randomly allocate people to treatments, that can lead to high levels of variation between units. And that might obscure the effects of the treatment of interest. And then if you group units or observations into blocks with similar attributes like location, time, age, sex, that can explain some of the variation, and it can lead to more precise estimates of the parameters that you're interested in. So blocking is something that might be unavoidable. So for example, if you're studying a treatment in different hospitals, and you have multiple patients from each hospital, then hospital is a blocking factor. The patients are blocked within hospital. So sometimes you can't help it. You have blocking in the way that your study is designed. Other times you can induce blocking if you want, or not induce blocking. That might be your choice. So instead of how does blocking relate to wanting independence of research? And as long as you're randomly allocating at some level, then there won't be independent, but you're going to take into account the dependence later on in your analysis. So if you have a blocking variable, you then use that in your analysis. Sorry, that was answering the question, how does blocking relate to wanting independence? So, so what you might do, for example, instead of allocating all patients randomly to treatments, you might block by some variable which you think will affect the outcome, like age or sex, and that might take away some of the variation. So I'll just keep going and get to the example, because that makes more sense once we have an example. So the way to increase power with blocking is to allocate treatments within blocks. So not across blocks, but within blocks. For example, in the patients in hospitals example, you would allocate each of the treatments to some of the patients within each hospital. So you don't say hospital A is in treatment 1 and hospital B is in treatment 2. You go to each hospital and some of the patients get each of the treatments. So you're allocating the treatments, all the treatments within the blocks. Of course, that's not always possible. And like I said, you have to take this into account. So yeah, by blocking, you are breaking the assumption of independence, which is not great, or it's fine if you take it into account, but it's not great if you don't take it into account. So if you're doing stratification or blocking, you take that into account in the analysis by adding either fixed or random effects as required. Okay. So here are some examples. So you're an ecologist and you want to do some treatment on leaves. So instead of just doing treatments randomly on different leaves of different trees, you block by tree. So you go to the same tree and you apply each treatment to different leaves on the same tree. And essentially what you're going to do is you're just going to compare how that tree responded to each of the 3 treatments, and the same for every other tree. So you're going to compare within tree, and that reduces the that gets rid of the between tree variation. Or if you have like a machine, a centrifuge, for example, and the different runs might produce different results, then you might want to put each of your treatment in each run so that you can control for the blocking of the machine, and that won't increase the variation between units. Or a person or an individual, like a person or a mouse, can be a blocking factor. So we can either sequentially apply all the treatments to each individual. Sometimes that's possible, other times it's not. Or a person can be their own blocking factor by looking at change from baseline. So you might take 2 measurements of each person, one before treatment, one after treatment. And then by looking at the changes within baseline, we get rid of a lot of the between person variation. Okay, so these are some ways to block for better power. So how do we randomize with blocks? There's this block RA function. We need a blocking variable. Okay, so we have this data set that has the hair color, eye color, and sex for 100 people. So this is the first 6 rows. So the first person has black hair, blue eyes, and is male. And we're only interested in the hair color at the moment. So the person, so there are 30 people with black hair, 21 with brown hair, 26 and 23 with those hair colors. So the treatment we're going to do is like give them, peroxide their hair. So they might have different reactions to the peroxide depending on their hair color. So hair color is an important factor in how they'll respond to treatment. Okay, so what we do is we use block RA, so a block random assignment, and we say our blocks are the hair variable, and we want 3 groups. And so then when we look at it, when we do that and we look at a table of the treatment by hair color, we can see that now we've allocated 10 people with black hair to each of the 3 treatments. There was not quite an even number of blonde people, so there are 8 in this group, 7, 8, but they're basically equally allocated to the treatments. And so that's nice because now we have equally, we've balanced the groups according to this blocking or stratification variable. So that's one thing to do. And then later on, we're going to include the stratification variable in our model, and that will account for some of the variation, so that we are essentially comparing the treatments within blocks rather than between blocks. Okay. So this is what it looks like in the data. So if you want to know which treatment the first person is in, they are one of the black haired people in the 3rd treatment group. So that's the treatment group for the 3rd. So you'll get this data set out and you know where to allocate everybody. Yeah, you could probably, so is it possible to block more sex than female and male, e.g. trans, non-binary group? Yeah, you can definitely, if you have enough people in those groups. You often don't. Oh, Nancy's answering questions. Nancy, can you just let me know if there's a question that you think I should answer? So I'll stop paying attention to the chat.
Will do.
Okay. So we've been able to, so we've allocated equal numbers to each of the treatments from the strata. If we'd randomly allocated, we'd also get approximately equal numbers anyway. This is why random allocation is usually is unbiased. It gives you the causal effect, because by randomly allocating, we would get approximately this distribution anyway. But we can do this block randomization where we get more exact equal numbers. Okay, we can do the same if we have unequal treatment numbers. So if we want more people in treatment 3, but less in 1 and 2, we just need to add a probability each statement to that, and then that will do that for us. Okay. Okay, so what about power? So blocking has a huge effect on power, or can have. So let's consider this experiment with 2 treatments. So when you're studying for an exam, what do you do the night before the exam? Do you rest? I rest. I never study the night before an exam. Or I try not to, unless I'm doing really badly in study. But if I've been studying all along, I don't study the night before, I just rest. But some people like cram the night before an exam. So which of these is a better strategy for taking tests? So you're an education researcher and you'd like to know. So you have enough funding and ethics approval to sample 50 students. That's all you can do. you have 50 students, and you have a choice. You can take students from any school in the country, and you can just choose 50 students at random in some way from the whole country. Or you can go to 25 schools, and you can choose pairs of students from 25 schools. And then you can allocate one of those students, one of the pair, to each of the treatments. So one of the pair will be told to rest before the exam, and one of the pair will be told to study before the exam. And this response variable is the mark of the student in exam. And what you're interested in, the effect size you're interested in, is to detect a difference of 4 marks. And people have taken this exam many times. So you've had a look in the literature, and you know that the standard deviation of exam marks is about 7 for this kind of exam. And you know that the correlation between students within a school for exams is about 0.6. So you have this information because, from the NAPLAN or something, you have an estimate of the correlation between students. So that's reasonably high. So what that means is, school has an effect on people's mark. And so 2 students within a school will tend to have a mark that's closer to each other than 2 students from different schools. So they're correlated to one another. And we're going to use this correlation to our advantage. Okay. So, our clinically meaningful difference is 4, that we said. We want a difference of 4 marks, and the standard deviation is 7. So I'm going to keep those things constant. And then I'll have a look at what happens if I just collect 50 students at random and allocate them to my 2 treatments. So not within the same schools, just from anywhere. Okay, so I've got 25 in each group. I calculate my standardized effect size by dividing the treatment effect by sigma. Significance level is just going to be 0.05, and I'm going to read power as null. So this time I want to know what the power is given my sample size, because I can't change my sample size. They've told me I have enough money for 50 students. That's all I can do. So I need to know what my power is. What's my chance that I'm actually going to be able to detect this difference? And if I do that calculation, I find that my power is 0.51. So about half the time, I will have completely wasted everyone's time and money. So my chances of actually getting a significant result, of getting a p-value that's small enough that I can then say, well, there's a significant difference between these 2 groups, my chances of that are about 50%. Even if there is a true difference between these 2 treatments, that is at least 4 or more. That is exactly 4, actually. So half the time I've wasted my time. All right, so then I tried the alternate sort of the different allocation. So I have to do a little bit of maths to do this in R, but it's not that hard. And you'll get my slides, so you can do it too. So it turns out that a paired t-test is what you would do when you have paired data, and a paired t-test is just a 1 sample t-test for the differences. Anyway, it's not important. You're still using the same standard deviation, but what we need to do is calculate the standard deviation of the differences rather than the standard deviation of each measurement. And so that's how we do that. It's not important. It involves this correlation coefficient. That's the important part. So we know that these students are correlated. Okay, so if we do that, we've now got this re-estimated standard deviation here. So the only difference is we've got that, and we've got type equals paired, and we've got exactly the same sample size, and our power is now 86 or 87. So I've got exactly the same number of students, and I've done exactly the same thing in every way, except that I've paired the students within schools. And I've done that because I know that students within a school are more similar to each other. So I've given the treatments within the blocks, and I've improved my power from about 50%, which is like a coin toss, to almost 90%. without costing me anything. So that's what you can do to improve your power. Presumably there are questions, but Nancy will let me know if I need to answer them.
Okay.
Okay, wonderful. Alrighty, so there are no questions. Okay, I do like to answer some questions sometimes. Okay. So then there's this like section on really advanced study design. This is just fancy stuff and it won't appeal to everybody here. But some people have already asked questions which are covered in here. So I'll go into that. So what if you want to calculate sample size for more complex analysis? So literally all I've shown you is a t-test, how to calculate sample size for a t-test. But what if you
Gordana,
have...
there is one quick question on the paired in the chat.
Would it work if I only knew that school influenced the outcome? It would still work. It depends how much it influences the outcome. So it would be hard to calculate the exact effect of that. Well, you wouldn't be able to calculate the change in power if you didn't know the exact effect of the correlation, or at least you couldn't estimate it. But often there's like, you can do like a proxy for it, you know, like there is often ways to like kind of get something from the literature which will give you an idea of how related things are within schools or within whatever blocking factor that you have. Otherwise, you try different values that you think are reasonable and see. You don't really lose anything from blocking, generally speaking. So you can just, yeah, if you think that there is, should I get the correlation from the literature? Yeah, that's a good place to get correlation. It's kind of hard to do. Often it's hidden in some other way. It's not exactly reported as correlation. If it is, you're very lucky. But yeah, sometimes it's hard to pull out and you might need help from a statistician. I'm just going to go off.
Gordana, there's another question in there.
N equals 25 refers to the number of schools that you've selected from students. Oh, okay. So sorry. So I should have pointed it out. So when I do this unpaired one, it says N is the number in each group. So 25 in each group. And then when I do this one, it tells you N is the number of pairs. So that's already taking into account the pairing. That's why I know. Does that answer? Yeah. Okay. So if I've only told you how to do a t-test, but you'd want to do some other thing like an ANOVA or linear regression or mixed model or survival analysis. Okay, so you have some options for relatively simple things like ANOVA. You can use the power package. There's ANOVA options there. Often what I would do is I try to simplify the main research. You usually have a primary research question, and sometimes it can be simplified to something approximately a t-test. It will give you an answer that, you know, power and sample size analysis is always approximate. You're never going to get an exact answer because you don't know. You're just guessing at a lot of these things. And so if you can simplify your question to be an ANOVA or a t-test, your main primary question, then that's one way to get an idea of sample size. But for more complex analysis, you might have to, well, the probably number 3 should become see a statistician. We have access to more advanced programs like PASS, which can do a lot more things than the sort of free programs that are available. For really complex things, what we tend to do is simulation. So if you're not an R person, you might glaze over at this point, but I'll give it a go for those who are interested. So the basic idea is you need a pilot data set so you can estimate variation. And then what you do is you fit a model to your pilot data, and then you simulate data according to that model, but with an effect size that you specify. And you do this many times. So you simulate as if from a population with that effect size, but the variation is estimated from the pilot data. And then what you do is each time you simulate a data set, you do an analysis, you see if you get a significant p-value, and you calculate what proportions give you a significant, what proportion of simulations give you the significant p-value. And this is an approximation of your power. Will you be discussing the difference between a one-way ANOVA and two-way ANOVA today? I will not. No. I've tried not to put any statistics, as in like statistical tests in here. I had to do the t-test, but that was the only thing that I was doing. Yeah, I just put the t-test in there so I could show you how to do a power analysis, but also so I could show you the thing about blocking and pairing in a real example. Okay, so this is, it sounds kind of simple, but it's quite difficult to do. So you need the pilot data. So this is kind of how it looks like. I've got this data set, which I'm going to fit a linear model to. And I have some data on some plants. And this is the length of the petal of the flower. And this is the length of the sepal of the flower. And my pilot data has 15 observations. And so what I do is I get my pilot data with 15 observations and I fit this model that I'm going to fit in the end to my complete data set. So the exact same model, the exact same analysis that I'm going to do. And I do that. So what I then do is I see what's estimated. So I've got, what I want to do is use this to estimate the things that I need. So one of them is the variability. So I want to estimate variability, and I can get that from the output of this model. It's just the sigma variance. I also want to get the intercept, because that's not what I'm interested in. Like, this is a linear model, right? There's an AX plus B component, and I'm really only interested in the effect of petal length on sepal length, so that the effect size is going to have to do with that gradient. And so that's what I'm going to focus on here. I'm going to simulate data 500 times for this analysis. And then I'm going to remember the effect size should be something meaningful, I don't want to estimate the effect size that I want from my pilot data, because that only contains 15 observations. It's not going to give me a good measure of effect size, nor is it what I want. So I want a clinically, ecologically meaningful effect size. So I'm going to set that to 1 in this case. So this is the slope. And then what I'm going to do is some complicated stuff. So if you're an R person, maybe you're interested. Basically, what I'm going to do is create a data set where I don't have sepal length. So my response isn't there. I just have petal length. And I'm going to simulate sepal length from that model here. I'm going to predict sepal length from petal length using that model. But I'm also going to predict it in such a way that it has uncertainty. And the uncertainty will be the variability that I estimated before. So I know that a linear model is just beta 0 plus beta 1 times petal length. So that's what I'm going to do in each simulation. And that's my mean. And then I'm going to add some error, and that error is going to have the same standard deviation as I estimated before. And then I'm going to, so I've got some simulated data here called sim data. And now I'm going to run my model on that sim data. So that's my simulated data. And I have to decide how big my simulated data is, so what the sample size is. So here I've decided that I want my sample size to be 20. So I'm going to simulate some data that has 20 observations. And then I'm going to fit the model that I want to fit to this data. And I'm going to see what the p-value is. And then I'm going to do this 5,000 times. And I'm going to see what proportion of my p-values are less than my cutoff. And in this case, it's about 50%. So for this sample size of 20, about 50% of the time I get a significant p-value. So that will be my power. So if this is all over your head, don't worry about it. But I wanted to put it in case people are interested in doing more complex power analysis. Okay. Another thing you might be interested in is factorial design. So maybe there are more than one, you're allocating people to more than one treatment. So in this case, people need to be allocated to 2 treatments, like 2 simultaneous treatments. One is a medication. This is like a study on depression. So the subjects are going to be given one of 2 medications, or at least, or one medication and a placebo, so one of those 2. And they're either going to be in counseling or they're not going to be in counseling. So they need to be allocated to combinations of these treatments. So this is what I would like. I've got 80 patients and I like 20 of them to get counseling and be in the active group, 20 in each of the subgroups. So how do I do that? Well, all I need to do to allocate people to these designs. So why would you do that? So factorial designs, if you allocate people to each of these groups, you find that you can estimate a bunch of things. So you can estimate all the main effects. So that means you can estimate the effect of the medication and the effect of counseling on depression. But you can also estimate interactions. So you can say, well, does the medication work better in the group that got counseling versus the group that didn't get counseling? Or does the counseling work better in the group that was medicated versus the group that was not? So you can estimate all of these things if you have a factorial design. So if you want to randomize people to multiple treatments, you actually just trick the same function that we used before. So I just made combinations of treatments. So this is active and yes for counseling. This is active and no for counseling. This is placebo and yes for counseling. This is placebo and no. So I actually just have 4 treatments. The software doesn't need to know that they're a factorial. All I need to do is do that, and that will give me that will allocate my patients to randomly to those groups. Okay, what about making sure that all their things are equal? So age, sex, etc. So you can, there are lots of ways to make sure that things are equal. So if there are relatively few things, so if you want your groups to be balanced by age, say, and sex, and you have a relatively simple idea of age. So maybe like below 40 and above 40, you want the groups to be balanced by below 40 and above 40, and sex. You can probably do that by stratification using the earlier stuff we did with hair. But if you have lots of variables, if you want your groups to be balanced by many, many variables, you might need to use a technique called minimization, I think it's called, where it tries to balance by many, many variables. That's much more difficult. But quite often, if you have a large sample size, you shouldn't really worry too much about things being equal, because by randomly allocating patients to groups, you will get an approximately equal balance. So it shouldn't be a big deal. It's only when the sample size is small that you might get big differences between groups, and then I would worry. Okay. Okay, so there's this idea of fractional factorial design. So say you have, I might actually skip that. Maybe I'll just skip that. We're getting a bit tired now, and I think I'm just going to skip that. It's a bit, maybe I'll do the Latin hypercube. Sometimes you want to sample in like an area, for example, or you want to choose people according to some criteria. And you want to do that in a more balanced way. So I guess we can think about this as an area. So this is latitude and longitude. And we only have 4 samples. So we're going to randomly sample in this area. We might end up with like a not quite balanced sample. So you might get clustering. So you can see that there's like 2 observations that have approximately the same level of B, but there's nothing kind of here. So you might wish that you had some observations in this area of B as well. So what you can do is these sort of Latin hypercubes where the space is kind of allocated into these sections. And then the idea is that there is an equal number of observations in all the rows and columns. So it's kind of like Sudoku, where we kind of spread out the observations in all the variables. And sometimes that's better when you have small sample sizes. So that's actually really easy to do in R. You just do this library Latin hypercube. And so here is an example of that, where you might want to, so I have a sample size of 10 and I have 3 variables. So here I have latitude, longitude, and height. So I'm going to sample like, I don't know, air pressure at 10 locations, and I need to know which locations I should sample at. So if I do this, I get sort of this idea. So here is the latitude and longitude, and so everything's kind of spread out. If instead I'd done a random sample, you can see that things are kind of bunched up over here, and there's nothing in this space here. So that's kind of what you can do if you want a more even sampling design. Anyway, I think what I'm going to do is finish there and just summarize what we've talked about. So the first thing to do is you have to define a really precise research question before collecting any data, before doing sample size, before doing a random allocation or anything like that. Before looking at your observational data, you need a research question that you can define very clearly. Ideally, you do a manipulative experiment. You have controls, replication, randomization, so that you can infer causation. And you can ensure independence by random assignment. And you can have a trial with high power. So you want to aim to have a trial with high power by looking at what the sample size should be. And you can improve your power for free by blocking in lots of situations. Otherwise, you might have to do an observational study. And if you do that, then you need to control for all your confounding variables. And one way to set up an observational study is to use a target trial as well. And then don't interpret your effects as causation if you can. And when you're doing your study design, ask for help early and often. We're here to help in this. And all researchers at UNSW and all research students at UNSW are entitled to study design advice from us for free. So we're very happy to do that for you. Okay, I think that will be that.
Thank you, Gordana. Now I'm going to open it up to specific and general questions. If anybody has any comments, please unmute yourself, maybe show us your face, or put your question in the chat.
Okay, so there's a question that says, what if the standard deviation of your 2 groups in your pilot study is different? What should we include in the power analysis? If you think that if it's really different, if it's a little bit different, then I would just take the average for the purposes of power analysis. If it's really different, then you can, you might, in the end, the sample that you get for your final analysis will probably also have a different sample size. So you wouldn't do a 2-sample t-test that assumed equal variance. You would do one that didn't assume equal variance. And so it's just slightly different tests, and you would then use that test for your power analysis. Any more questions? Feel free to unmute yourself. I've been talking for an hour and a half. I could definitely use hearing another voice. All right, seems like we're all out of questions.
Thank you so much, Gordana. Thank you so much for your presentation. Just to let everybody know, we will put the video of this available on our website, so you can watch this again if you'd like, or share it with your friends. Thanks for coming, and just to let you know, our next monthly seminar is June something or other. Sometime in June, we're going to be talking about how t-tests are linear models. So please look out for the Eventbrite page for that. Thank you so much.
Thank you.
Thank you.